All right, let's talk about a fundamental mismatch in how our computers see the world. You see, they tend to see things in these rigid, separate snapshots, these jagged little steps. But what if we could teach them to see reality the way we do, as a continuous, unbroken, smooth flow? Well, today we're going to dive into a pretty revolutionary AI technique that does exactly that.
It really starts with this question. How do our computers see time? The real world, the physical world around us, it's just this seamless stream of events, right? But for the longest time, our digital models have had to chop that reality up into these discrete, separate moments. And that creates a huge disconnect.
And this slide really lays it out. On the left, you've got that digital view, a world of jagged steps. That's how most of the AI models we've used for years, like recurrent neural networks, have to process time. But on the right, that's reality, a smooth, continuous flow. The whole goal of what we're talking about today is getting our AI to jump from the left side of this slide over to the right.
And this is where even the heavy hitters of AI kind of hit a wall. I'm talking about incredibly powerful models like RNNs and transformers. They are just fundamentally constrained by seeing time as a series of fixed steps. Now that's fine if your data is super clean and regular, but they really struggle with the messiness of the real world. Think about a patient's health chart, where you get observations at totally random, irregular times. These models have no idea what happens between those data points.
So if that's the problem, how do we fix it? Well, the answer isn't just a small tweak, it's a major paradigm shift. It's about moving away from those discrete little updates and instead embracing the mathematics of continuous change. This is really the big aha moment.
And the solution is this beautiful fusion called neural differential equations, or NDEs. Instead of just playing a game of connect the dots with the data, an NDE learns the underlying laws of physics that govern how the system evolves between the dots. It's actually learning the function of change itself. Pretty cool, right?
But here's the thing. NDE isn't just one model. It's actually a whole family of different approaches. So to really get what's going on, we need to break down the three key branches of this family tree. Each one tackles the problem in a slightly different and more powerful way.
So first up, we have neural ordinary differential equations, or NODs. This is kind of the granddaddy of the family, the foundational model. It learns a single deterministic rule for how a system is going to evolve. So once you know the starting point, the entire future path is basically set in stone. Think of it like a ball rolling down a perfectly smooth, predictable hill. Next, things get way more dynamic. We've got neural controlled differential equations, or NCDs. Now the model's evolution is actively controlled or steered by a stream of data as it comes in. So unlike that fixed path of an NOD, this is more like a path you can actively steer in response to new information. Now keep this one in your back pocket. It's going to be our art critic in just a minute. And finally, we get to the star of our show today, neural stochastic differential equations, or NSDEs. This model is the one that really embraces the chaos of the real world. It actually adds a random component, what mathematicians call Brownian motion, right into the mix. And this lets it model not just one single path, but a whole universe of possible, noisy, unpredictable paths. This is going to be our art forger. Okay, so we have this incredibly powerful tool for modeling randomness. But, and this is the big question, how do you actually train it to be realistic? Well, the researchers here came up with a brilliantly clever solution. You make it play a competitive game against another AI.
Really think about that for a second. This is the crucial question. It's one thing to follow a path, but how do you teach a machine to generate a whole bunch of new believable paths that capture the true randomness of a system, like the flicker of a stock price or something?
Well, you do it with a generative adversarial network, a GAN, and the setup is just perfect. Our neural SDE, the one that can handle randomness, plays the role of the art forger. Its only job is to take random noise and generate fake time series data that looks completely and utterly real. And our neural CDE, remember that one? It plays the art critic, or the discriminator. Its job is to get incredibly good at spotting the forger's fake.
So the training process becomes this constant battle. First, the generator, or forger, takes some random noise and makes a fake path. Then, the discriminator, our critic, looks at that fake and real path and has to decide which is which. Based on that feedback, both models get smarter. The generator tries again, making an even better fake. The discriminator also learns, getting better at detection. It's this constant cat-and-mouse game, round after round, until the generator gets so good that its forgeries are statistically indistinguishable from the real thing. So, does this whole theoretical cat-and-mouse game actually work? The results are, well, they're pretty stunning. Let's take a look.
And this image just brilliantly illustrates the outcome. The blue lines you see here, that's real data from a complex, random process. The red lines, they are completely synthetic, created from scratch by our trained art forger. I mean, look at them. Notice how they capture the drift, the volatility, the whole feel of the real data perfectly. It's almost impossible to tell them apart.
And this right here is what proves the model isn't just memorizing or cheating. Look at the distributions on the left. This is near the beginning of the time series. The real data and the generated data are a near perfect match. Now look all the way to the right, far into the future. The match is still incredibly strong. This tells us the model has learned the true underlying rules of the system, which allows it to project forward with real confidence.
And you know, the best part is, this isn't just some academic exercise locked away in a lab. This tech is being made accessible to everyone through open-source tools. This quote is the tagline for a library called Torch SDE, which puts these advanced solvers right into the hands of developers.
And check out how simple it can actually be to implement. With just a few lines of Python code using that Torch SDE library, you can define and solve one of these complex stochastic differential equations. This accessibility is really what's going to drive the next big wave of innovation in this space.
So, let's step back for a second. What's the big takeaway? Why does all this matter? Well, this isn't just some clever trick. It's a whole new frontier for modeling any system that evolves with uncertainty. We're talking about everything from the chaos of financial markets to predicting disease progression from irregular hospital visits. It's a bridge between centuries-old mathematics of change and the massive power of modern neural networks.
And all of that leaves us with one final fascinating question. Now that we have the tools to genuinely model and generate data from these complex, chaotic, continuous systems, what should we point them at next? The possibilities, I mean, they're truly endless.